So now that we have a virtual substrate, which is essentially a silicon wafer with some buffer on it that allows us to grow the pure germanium quantum well, we can talk about the quantum well itself. The quantum well is not grown directly on this virtual substrate. In some cases, maybe the virtual substrate is provided commercially and you don't want to put your sensitive quantum well directly on a wafer that's been sent to you by some postal service. In other cases, even if we grow the quantum well directly in the same growth system that we just grew the virtual substrate, it's helpful to grow this part of the structure at a much lower rate and a much lower temperature. Much lower rate so that we have better control of the interfaces, and a lower temperature because in this way we avoid interdiffusion, relaxation of these sensitive layers. So it's normal that we grow some kind of barrier which can be 100 or 200 nanometers thick, and this gives us some space and time to lower the growth rate, lower the temperature, and let everything settle down. And then once we're suitably far away from the virtual substrate and its associated defects, we finally grow the quantum well, and the quantum well needs to be between 15 and 20 nanometers thick. A quantum well is defined by the fact that the wave function is confined in the vertical direction, so shorter than the Fermi wavelength. And then another critical parameter, not just that the quantum well needs to be thin enough to be strained and also thin enough to behave as a quantum well, is the cap thickness between the quantum well and the surface, or the surface of the semiconductor. And this is relevant, as we will see, because it controls the operating range over which the quantum well will work. To make the quantum well work, since this structure has no doping inside, so there is nothing here to provide charge carriers, the charge carriers are induced by the field effect. So on top of the semiconductor, which is capped with some sacrificial silicon layer, which can then oxidize in air, some kind of oxide is deposited, and so far we are mainly using aluminium oxide. And this is deposited by some kind of atomic layer deposition method. And on top of this, the gate metal, which is then contacted, and the gate bias is applied, and a negative gate bias will pull holes into the quantum well. We can see this if we look at the band diagram of a quantum well. So the solid black line in this case is the heavy hole band. You'll see that the heavy hole band is split quite far away from the light hole band, which is a dotted line, and it's the strain in the quantum well which is creating that splitting. And there is some splitting also in the barriers, because in this case a realistic structure will have a slightly different composition between these layers because they're grown under different conditions. A little bit of strain-induced splitting maybe in the barriers, but a lot of strain-induced splitting in the quantum well. And you can see in this case the heavy hole band is reaching roughly where the Fermi level is, but not enough to actually induce a carrier gas in the quantum well. So in the case of not applying a gate bias, there are in fact no carriers in the quantum well. This is an advantage because this means that we will be able to define quantum dots in these quantum wells by biasing more positively or even at zero, so there are no holes in the quantum well, and we can isolate parts of the two-dimensional hole gas. As we start to apply a negative bias, you can see that the wave function starts to populate in the quantum well. And of course, what you can see is because these particles are charged, they actually create an electric field. So the electric field in the cap between the gate and the quantum well is proportional to the charge density in the quantum well, which is the same but opposite as the charge density on the gate. And this is important because then you can see that the bands are bending as we go from the cap down through the quantum well and then beyond down into the substrate. And this is very important because there's no way to have charge in this system without having an electric field, and the electric field is changing the potential. This means that the quantum well is not the square profile of the germanium which was grown, but actually a triangular well created by this change in electric field. And so you can see the wave function there is concentrated towards the upper interface. If we go on to apply a very strong bias, you'll see that eventually we're limited in how many holes we can put in the quantum well. The problem here is that once the valence band at the surface reaches the Fermi level, then the surface channel is going to start to populate. And even if that's maybe not a mobile channel because that's silicon germanium and it's a imperfect interface, so it will have a very low mobility, even if that doesn't necessarily electrically conduct, it will start to screen what happens in the quantum well. So it will reach some kind of limit about what can be achieved in the quantum well. So the past 3 slides demonstrate the operating range over which the quantum well will work, in between being switched completely off and being saturated, and then the surface channel being saturated such that the quantum well has reached its maximum density. We can estimate this maximum density if we consider a little bit the valence band offset between the quantum well, the pure germanium quantum well, and the cap, and we look at the spacer thickness. And there's a very simple calculation that just basically says the electric field is the valence band offset divided by the cap thickness, and that's proportional.